So, hello guys, nice to meet you in Calculus grade 12 classes. Today we have class number 13 and we're going to continue discuss the topic with the general name curve sketching. Today we're gonna talk particularly about unit 4.2, and in today's class we're going to discuss quite a few more properties of derivatives that can help us to identify critical points on the curves. And I'm going to explain you what is that exactly in just in a minute. So let's take a look at this sketch. Here we can see two parabolas, right? One of them looking upwards, the other one looking downwards. We can clearly see that on the one that looking upwards, we are given with local minimum, and the other one that looking downwards, we're looking for local maximum. So in chapter 3, we learned that maximum and minimum of a function value might occur at a point, some constant, comma function of this constant, if derivative of this function at this point equals 0, right? Guys, work with me?
Yeah.
So we also solved couple examples where derivative was equal to 0, and we showed that it was local minima and local maxima. Can you remind me what we took as a reasoning for that? Don't worry, we're gonna stick to this for quite a bit time. So, what's your idea? What we're looking at?
The reason for what? Sorry?
Reasoning for this point to be local minima or local maxima. It's not just that derivative equals 0. There is one more crucial factor. We were looking on the sign of a derivative, right?
Yeah.
We determined that if it's local minima, then the sign of the derivative before this point is going to be negative, because function is decreasing, and that's part of a slope, right? To the left-hand side, to this vertical line that I just drew. And to the right-hand side, we can see that function growing, so derivative sign is always positive.
Yeah.
And based on this relation that particular based on that initial function is decreasing before this point and increasing after it, states that it's a local minimum for us. On the other hand, if we know that function was growing before this point and it decreases after, it's a local maximum. Am I right?
Yeah.
So, but what are we gonna do if derivative, for example, has no zeros, like never equals 0, or it equals 0, but it's not local minimum or local maximum? So it is also possible that maximum or minimum function value might occur at a point where we still take some constant function from this constant, and derivative at this point is undefined. Remember, we had we discussed about derivatives, when do they exist, as well as domain of a function may be limited due to cusps, breaks, jumps. Remember, we discovered 3 types of problems that we may face: when function goes to the infinity in a point, when function breaks in a point, when function does not exist in a specific point, thus derivative would not exist in this point. Do you recall that?
Yeah.
Kinda. So that's where we're going to implement it. It's not just some kind of graphics that we cannot visualize because they have no derivative at this point. that thing that they don't have derivative at this point actually also gives us information about the initial function. Okay?
Yeah.
So even if derivative is undefined at this point, let's say we found a derivative that looks something like x 1 over x plus 1. And this is function of the derivative, right? So this function would be undefined in the point x equals -1, because the denominator turns into 0 in this case, and the whole expression would result in uncertainty in terms of infinity. Am I right?
Yeah.
So we cannot say what value derivative takes at this point, but we know that when x equals -1, it still would be the critical point, and we're going to talk about them today. And value c, in this case, c would be -1. This is c when derivative is not defined. So undefined, basically. Do you see this? Please look here. Point C, comma, f of c. So if, for example, my point was somewhere here, her coordinate would be c on the x-axis and FOC on y-axis. Am I right?
Mm-hmm.
At the same time, f prime of c, so if I'm taking derivative of my initial function in this point, it would mean that this derivative is undefined in this point. Like example I just showed you, I took c equals -1 and my derivative is not defined because I'm getting infinity. Is it clear?
Yeah, kind of.
So please try to understand that critical points, they help us to define the shape of the function graph, and values of c or x value at this point it is called critical number. So combining this with properties of increasing and decreasing functions, we have a first derivative test for local extrema. Okay. So for example, with this two parabolas, we already discussed how we would test it for local minima or local maxima, right? Or in other words, local extrema. Let me move on to the next slide. Just a second. So yeah, here is the reasoning that we talked through together. So if f prime of x changes sign from negative to positive at x equals c, then f of x has a local minimum at this point. Makes sense?
Oh, okay, yeah.
Negative to positive, boom, local minimum. If derivative f prime of x changes sign from positive to negative at this point x, then f of x has a local maximum at this point. And you see that this is where this point comes, c. So f prime of c equals 0 may imply something other than the existence of a maximum or minimum at x equals c. Because remember, what it means that derivative equals 0? Tell me, guys. Tell me geometrical geometrical interpretation of a derivative. When we finding the derivative, what exactly is it in terms of graphing, plotting on the, you know?
Finding the tangent line of the
Exactly, that's absolutely correct. And
Yeah.
the tangent line has a slope equals 0. What does it mean?
It's at its maximum or minimum, or it's
No, 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 no.
whenever tangent lines at 0.
So
What?
derivative equals 0 stands for the angle of a slope, right? So if basically we say that the slope of a tangent line equals 0, we know that it's going to be a horizontal line, right?
Mm-hmm.
And it's going to be tangent. And basically that's what it says. If derivative equals 0, you're going to have a horizontal tangent line to the curve, right? But the fun fact that not every tangent line that is horizontal to our like initial function is going to state for the local minima or local maxima. For example, a simple function that you may have faced is x to the third power. X to the third power, I would plot as this type of sketch, you know, that passes through 0, 0 point. For all negative values of x, it's decreasing to the bottom, and for all positive values of x, it's going to increase to the minus infinity. First of all, you can see that this point, when my function passes through 0, 0, is going to have a tangent line, horizontal tangent line. Let's show that, okay? Let me find the derivative of my function. That is x to the third power. Can you remind me, guys, what would be my derivative?
Would be to 3x
3x
squared.
Perfect. So first things first, I see that when x equals 0, my derivative, f prime of x, also equals 0, right? Guys,
Yeah.
when I substitute x equals 0 in this equation, I'm
Yeah.
gonna get derivative equals 0, right?
Yeah.
So in another, I'm sorry, in other words, based on what we learned before, you would say this is local maxima or this is local minima, right? Guys, let's work
Yeah.
together. So now look at the graph. Does this look like local minima or local maxima to you?
No.
And you're absolutely right, because this is neither minimum, neither maximum value of a function, right? In the whole domain. And we know that the tangent line at this point would be horizontal, right? It would go like this to this point. Am I right?
Yeah.
Mm-hmm.
So it wouldn't be inclined. And another fun fact that you can see here by analyzing the derivative function, does it ever takes negative values? Does the derivative ever equals minus something?
No.
And what is your reasoning?
Because you plug in -1, the squared would.
What if I plug negative million? How do you know that if you plug negative million, nothing changes?
Because if you square a number times a negative times a negative is a positive.
Absolutely. Yes, that's your reasoning. Good job, Alan. And you have to say that if our variable is squared, no matter what x value we take, it's always going to be positive or 0, right?
Oh, okay. Yeah.
So there are other cases when even if it's squared, it cannot be equal to 0. I don't know, maybe. But in general case, if anything squared, it's always going to be positive. If anything raised to the odd power, you see this? Not even power. It's gonna have negative values in minus. Does it make sense?
Yeah.
So x to the 4th power, would it be always positive?
Yeah.
X to 5th power?
No.
Absolutely.
No.
Great. So keep in mind, this is very useful analyzing technique that we're gonna use a lot. So first of all, sorry, I moved too quick. We defined that this function never decreases. It's always growing, right?
Yeah.
Okay. And reasoning for local minima and local maxima is that function should decrease and increase before and after this point for it to be a local minima, and it should increase and decrease before and after this point for it to be local maxima. If we don't see this change in a sign of a derivative before and after this point, it means we don't have local minima or local maxima, but rather than that, we have a critical point.
Okay, yeah.
So there are also simple functions for which the derivative does not exist at certain points. Remember, we talked about them, like infinity. For this function, if it travels to infinity when x equals 0, for example, derivative would not be defined at this point, right? And if you find derivative and you get something like 1 over denominator x plus 1, you should know that whenever this derivative is not defined, so for this case, it's x equals -1. In this point, you should study the function more precisely, because in this point, you're going to have some specifics, this critical point, so-called. And we use them a lot in my time to sketch the graphs of complex functions. So let me clear this slide. Can we move on to the next one?
Yeah.
So extrema could occur at points that correspond to cusps and corners on a function's graph, and in this case, the derivative is undefined. So yeah, remember we had functions to graph that were restricted in certain domain from x1 to x2. Am I right, guys? Remember this?
Yeah.
So
Makes
let's
sense,
say
yeah.
my graph would look something like this. Here you can say like, oh, we have local minima. This is where function takes the minimum value, right? But if you look here, you see this point is going to be like dotted because it's on the line that we are not taking into the, for example, into the domain. And you can see that local maxima would not be anywhere near derivative equals 0, right? Local maxima would be on the edge of our domain. And on the edge, we cannot find derivative, remember? Because derivative is directly connected to the limit. And definition of a limit, existence of a limit. Do you recall it?
Yeah.
I'm gonna say it. The limit at a point exists only if we approach this value from left and right, we're still getting we're approximating to the same value. right? So the limit to the left-hand side and right-hand side from our point as we approach it. Limits are should reach one value in the middle, right? L1, L2, and they all gonna reach to value L, so they're gonna be equal. Remember, we had the point 2, 1.99. Here it was 2.1 for an instance, and we studied how limits are acting to left and right from this point. If limits from the left, for example, -1,000, and to the right it's +1,000,000, limit does not exist in this point. Is it clear?
Yeah.
Yeah.
So if limit does not exist, thus the derivative does not exist, right? And because derivatives are basically raised on limits. Remember, we did it together. And here on the edge of a domain, do you think derivative is defined?
Where are you talking about?
Right here
Oh,
on the edge of the domain. Does the derivative define?
no,
Why?
because there's no right side of the graph.
Absolutely right. So we cannot evaluate how function x to the right from this point. Thus, we cannot differentiate it in this point. And furthermore, if this point is like is not in the domain, even that, how we can define derivative in a point where function is not defined? Make sense? So let's move on. Let's practice connecting the first derivative test to local extrema of a polynomial function. For this point, function determine all the critical numbers, determine whether each of these values of x gives the local maximum or local minimum, or neither for the function. So guys, please go ahead and take your copybooks. Are you ready to write down?
Yeah.
Beautiful. So right now, one thing that we definitely gonna need to do with this function, as soon as it's derivative test, I want you to differentiate this polynomial function. I'm gonna do it with you. So here we have 8 times x to the third power is gonna be 24 times x squared plus 36 times x. Let me know once you're finished. Once this is in your copybooks, we can move on. I've seen somebody joining us. I just can't stop sharing the screen because I cannot see participants otherwise. Is anybody with us? Anybody new? Ahmad. Okay, feel free to ask whenever you have questions. And today we're discussing the advanced curve sketching based on properties of derivatives. So guys, how's it? Hello, Ahmad. No worries. You can text. So Alan, Yusuf,
I'm just
Yeah.
copying down the equation or like
Me
the
too.
example.
Pardon?
I'm copying down the example.
Okay. So can I continue?
Yeah.
Can you give me a second?
Yeah. So with this function, next step for us, this is derivative of y, right? Y differentiated once. And now we have to, let's remember what critical points are. Critical points is such a point when derivative equals 0 or derivative is undefined, right? So I need to evaluate when this derivative equals 0. This is the easiest way to start. And I'm going to do it by factorizing my expression. Here I can clearly see that I have x multiple in every one of them. Furthermore, I have 4 as a multiple in every one of them. So I'm going to factorize it by 4x. In the brackets, I'm going to have x squared subtract 6, x plus 9 plus 9. Am I right?
Yeah.
And next, we can simplify it even further, because this looks to me like perfect square, doesn't it?
Yeah, it is.
So it's going to be 4x times x subtract 3 squared. And now we can pretty easily define x values that we are interested in is when this whole expression equals 0. So such points would be x1. Based on that it's a product, I'm going to say that's 4 times x. If it's equals 0, then the whole expression equals 0. So x1 equals 0. x2 would be 3 in this case. When x equals 3, again, this term is going to be negative. Oh, it's going to be 0, sorry. Make sense? So I define my 2 x values, or remember, this is this C points, right? Guys?
Which
Yeah.
ones are the C points?
x1 equals 0 and x2 equals 3.
Yeah.
Okay.
So let me move to the next slide. Here's the solution they suggest. You see, it's same
Yeah.
step up to now. But this is not it. This is not all we have to do. Because once we found these critical numbers, x1 equals 0 and x2 equals 3 are critical numbers, okay?
Yeah.
We found them from reasoning that derivative of y by x equals 0. So both values of x are in the domain of the function, gladly, right? Because initial function is defined on the minus infinity to plus infinity. We don't have any problems. So first of all, these points are in the domain. That's the first thing that we have to check, right? Because what's the point of your critical point if you were asked to find it in the domain that it does not belong to? If it's not in the domain, then why is it for, right? So both values of x are in the domain of the function. There is a horizontal tangent at each of these values of x. Why? Because derivative equals 0. It means the tangent line would be horizontal, parallel to x-axis. Is it clear?
Yeah.
To determine which of these values of x yield local maximum or minimum values of the function, we use a table to analyze the behavior of derivatives and initial function. We started doing kind of this table in the last class. Do you remember? When I showed you, you can list plus and minus, whether a function is positive or negative. Then you can say if it's plus, then it grows. If it's minus, then it decreases, right? So can I clean this? Did you found this derivative?
Yeah.
Perfect. So this is example how it would be better for you to plot this table. So remember when we were looking for the sign of a derivative, we were taking intervals before and after the critical points, right? In between critical points as well. And after critical points. Is it clear?
Yeah.
Mm-hmm.
So here, what they're doing for x subtract 3s square, it's a product terms, right? So for x is going to be negative when x less than 0. It's going to be positive when x between 0 and 3. And it's going to be positive when x greater than 3, right?
Yeah.
The second product term that we have is a complete square. So it's as soon as it's complete square, it's always going to be positive, right? Don't even think about it. It's always positive because it's squared, right?
Mm.
So now we're looking into product of these two functions together, and we're basically looking on product of the sign, both of them. In this particular case, if x less than 0, you see we have negative value for first product term, positive for second one, which results in total a sign of the product as minus. Make sense?
Yeah.
So here we have product of two positive terms. So it results in positive product, as well as here, right? Positive, 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 negative. Remember we did exercise where we had 3 brackets and we evaluated whether they all plus or they were plus, minus, plus or something. Then we multiplied them. And if at least one of them is minus, it means the total product would be negative. If 2 of them are minus, it means, and third one is plus, it means the product would be positive. Make sense? Because negative times negative is positive.
Mm-hmm.
Here they didn't show this example, but it's just a common math. And here we say the derivative is negative because this sign is minus. Here we say derivative is positive because it's positive, and here it's positive again, right? So we also say that when derivative is negative, our initial function is decreasing. When derivative is positive, our initial function is increasing. And when derivative is positive again, it's still increasing. So what I see right away that before that when x less than 0, my function is decreasing. When x is greater than 0 and less than 3, it's increasing. And when x is greater than 3, it's still increasing. But you see, I had a critical point at x equals 3, right?
Yeah.
And my function increasing before x equals 3 and after x equals 3, which means there is no local minima, no local maxima. Make sense, guys?
Yep.
Yeah, it does.
So on the other hand, when x less than 3 is than 0, my function decreasing, and when x greater than 0, my function is increasing. So I'm gonna have local minima in this point, decreasing, increasing, minimum, increasing, decreasing, maximum. So using the information from the table, we see that there is a local minimum value of a function at x equals 0, since the function values are decreasing before x equals 0 and increasing after x equals 0. We can also tell that there is neither a local maximum nor minimum value at x equals 3, since the function values increase towards this point and increase away from it. Can we move on?
Just copying down the graph right now.
Pardon?
I was just copying down the chart.
Yeah. So crucial. Can you see my screen?
Yeah.
Oh, for some reason it was paused. Let me start again. So first thing first that we are looking for, all right? First line, first row is going to be intervals. Our intervals are defined by critical points. If you have 2 critical points, how many intervals are you going to have? Guys.
3.
Exactly. If you have 3 points, how many intervals are you going to have?
1, 2, 3, 4, 5. No. 1, 2,
1,
3,
2,
4.
3, 4.
Yeah.
And if we have 4 points,
5.
exactly. So you can see the pattern that number of intervals is going to be always +1 to the number of points. Second line, you can do this. You can list each product term separately and define its sign first and then write the product sign, right? But you can also do it in one step if it's easier for you. If you just see if it's completely clear, like a blue sky to you, that function would be decreasing or increasing in this range, you should just state the sign of expression, right? Like this. You can skip these 2 lines where they define the sign separately, and you can just leave this 1 line. But of course, for your convenience, you can still write them separately. Then you should say number 3. Number 3 crucial line is, number 1 is an interval. Number 2 crucial line is sign of the derivative. Number 3, value of the derivative. You're basically saying what it means. Negative means less than 0, positive more than 0, okay? It's important because you're looking here to say that my initial function, which is line number 4, you see this is not derivative, this is initial function. And we're saying whether we're decreasing or increasing. And number 5, schematically show the shape of the curve. Like it's going to go down or it's going to go up. Or another thing I do, I just mark them as an arrows. They're going up or down.
Can you go over the derivative one again?
Pardon?
The derivative one, the dy over dx. That step, can you go over how you get those?
Oh, this one, number 3?
Yeah.
So this step is basically based on the previous one. In previous one, we found that this expression is always going to be negative if x less than 0, right? And this is our derivative, right? So if derivative always has negative sign when x less than 0, it means it's going to be negative. Value of the derivative is going to be negative. In other words, less than 0.
If you plug in a negative number there, it's going to be negative?
Yes, if you plug in any negative number, it's going to be negative.
And then for the one next to it, if you plug in any positive number, it's always going to be positive?
Yes, absolutely. Because this product term is always positive for positive values, right?
Mm.
It would be always negative for positive values if coefficient would be negative. But now coefficient is positive.
Mhm.
So, and this is also always positive. This is just always positive because it's squared.
Mm. Okay.
So derivative would be always positive for values between 0 and 3, and would also be positive between values from x greater than 3. But take a look. Does it says less or equal?
No.
Absolutely, because when x equals 0 or equals 3, our derivative equals 0, and it's a critical point. Can I move on?
Yeah.
Yeah.
So this is how this graph looks like. And now you can clearly see what happened here. So this was your 0, right? We can see that our function decreasing and increasing after this point.
Mhm.
So it's local minima. And this is, I believe, where x equals 3. You see, we have horizontal tangent line that has slope equals 0, right? But it's neither local minima, neither local maxima. Because before and after this point, function is growing. Here, on the other hand, we had it decreasing and growing, so it was local minima. Is it clear, guys? Any questions so far?
No, I think it's
So,
pretty
so
clear
would
so
the,
far.
so then would the answer, the question has to determine whether each of the values of x gives a local minimum max a value?
The
Yes.
question was, let me move back, but the question was to define critical points and define whether this critical point gives us local maximum, local minimum, or neither for the function. So we show that 0 gives us local minimum and 3 gives neither.
Yeah. Okay.
So 0 and 3 are both critical numbers,
Mhm.
but 0 is local minima and 3 is not.
Mhm.
Is it clear, guys?
Yeah.
Example number 2. Reasoning about the significance of horizontal tangents. So basically, that's just part of what we just did. Here is x to the third power that I gave you as an example at the beginning of the class. So you have to determine whether function has maximum or minimum at this point. So at this critical point when derivative equals 0. And we already showed that there is such point that x equals 0, right? Right here, x equals 0. X equals 0, guys. Do you see it?
Yeah.
This would be the point where we have horizontal tangent line. And you already know reasoning about local minima or local maxima. So would you say this is any one of that?
This one's neither.
Exactly. From the graph, it's clear that 0.00 is neither a maximum nor a minimum value, since the values of this function are always increasing. And note that derivative is always positive for all values of x. Do you know why?
What's the question again?
Derivative is always positive for all values of x other than 0.
That's true.
Why?
Because if you look at the values greater than 0, so above the x-axis, it's constantly increasing.
not exactly what I was asking, but you're right. It's increasing after x equals 0, but it's also increasing before x equals 0, right?
Yeah,
Am I right?
yeah,
It's increasing constantly. And derivative of this function would be 3x squared. And why is it increasing constantly? We just discussed it at the beginning of the class. Because derivative is always f prime of x, always greater than 0.
yeah,
Or equals to 0, okay. But when it equals to 0, we know we're gonna have critical point, but if it's greater than 0, it means function always grows. And it's because of the power that it's squared, right? And why is it squared? Because initial function has the third power. Remember, derivative would always have power -1.
Can I
Can I
ask,
move? Yeah, sure.
the horizontal tangent at 0, 0, is the critical point our horizontal tangent?
Yes. Our critical point is 0, 0. Our critical number is x equals 0.
Okay, so critical, so then our critical point is always the y value,
Pardon?
critical number, sorry,
Critical number is always x value.
x value,
Yes.
then what's the y value again?
Y is just the value of function at this point. And critical number is x at this point.
So it gave us f prime of x equals 0, so that's how we know.
Yes.
Okay,
So it gave us f prime of x equals 0, so we know this x is a critical number. And also, if, for example, f prime of c is undefined, right? If my derivative is undefined in this point, it would also state for critical point. So we have two criteria for critical point. F prime of c equals 0, or it's not defined.
okay.
Is it clear?
Mhm,
yeah,
Can we move on?
yeah,
mhm.
So what we learned from this example, we can see that it is possible for horizontal tangent to exist when derivative equals 0, but that this point is neither maximum nor a minimum, right? In the next example, you will see that it is possible for maximum or minimum to occur at a point at which the derivative does not exist.
yeah,
Let's take a look at this example. We have to find the derivative of this expression anyway. So let's do it. That's would be most likely your first step all the time. Find the derivative.
Mhm.
Does anybody wish us to explain the solution of this example?
Okay, I'll try it.
Only part where we're defining derivative, then we're going to discuss it together. So
Okay.
you can draw here.
You'd move the exponent out to the front, and then you do your power rule. You subtract 2/3 by 1, you get -1/3.
Is it only the power rule that we have to apply here?
Yes.
I can't agree with you. What if I had x squared here inside? X squared plus 2.
Oh,
So it's a chain rule as well.
Hmm.
Am I right? Because remember, chain rule is whenever we have inside and outside functions.
Yeah.
When we deal with composite functions.
Mhm.
And this is a composite function. You got I think you got tricked by that. We don't have any additional multiplier, right? It's only power 2/3. But in fact, you're multiplying by 1 because derivative of x plus 2 is 1.
Okay.
So yeah, go ahead, please.
So you'd use a chain rule. You get the so then you put the 2/3 out in front, and then you subtract the power by 1. You get negative 1/3. You'd use your chain rule to get your g prime of x, which is 1. Put it out, multiply it. It'll just be the same thing, so you don't have to write it out. And then you can't have a negative exponent, or you want to simplify it. So you could drop that to the denominator. That switches to positive, and you get 2/3 x plus 2 1/3.
Great stuff, Alan. Good job. And here you're gonna see why it is so important to simplify your nominator.
Yeah.
You see, if we would just leave it like that, you'll be, oh, x equals -2. Derivative equals 0, right? 0 times 0. Or 0 times 2/3 is 0, right, guys?
Yeah.
But in fact, if you simplify it, then you can see, wait, -2 doesn't give me 0. In fact, it gives me, it makes this derivative undefined in this point, right? Do you see this? If I substitute x equals -2 in here, the denominator is going to be equal to 0, right?
Yeah.
2/0 is one of those cusps, problems that we can face. Am I right?
Yeah.
In other words, derivative is not defined in this point. On the other hand, when does derivative equal 0? Can you tell me?
This derivative equals 0. Is it just -2?
We just said that it doesn't equal 0 when x -2. When it's x -2, derivative is undefined.
Yeah, undefined. And when it equals 0?
When it's equals
2.
0,
Oh, no, -2. Wait. No.
I'm gonna make it easier for you, and I'm just gonna say it never equals 0. Because no matter what you put into the denominator, if your denominator is not 0, you cannot make it 0.
Mm-hmm.
Am I right?
Yeah.
Because no matter how many times you divide something, you're always gonna have fracture of initial number, right? It's so I would say as x travels to point -2, my function would travel to the value of I believe it's gonna be positive infinity. So you see, before -2 and after -2, we certainly have some values. But in -2, we have 2/0. So it's going to be infinity. Right?
Yeah.
So let's move to the next step. We found this critical point. Remember, critical point is also the point where derivative is not defined. And this is exactly example. -2 is our critical point.
Is-
So
Is that x equals -2?
it's x equals -2. It's going to be
Okay.
our critical point.
Is x and
So-
c equal? Like c is equal to x?
C is just a name for critical point, right? How you denote them in terms of letters. And we say that the oh, sorry, it's not a critical point, it's critical number.
Yeah, critical number, sorry.
Yeah, critical number. So x is what values of x when derivative equals 0 or derivative is undefined are values called critical numbers.
Okay, so x is equal to 0 then? No, x is equal to c, critical number is equal to x. Can I write that out or no?
I didn't really understand.
Is the critical number equal to x then?
No, not to all x's, not
to
all x's, but
Okay.
x's, specific x's, when derivative equals 0, your derivative does not equal 0 for all x, right?
Okay.
It equals 0 for one specific x, maybe for two x's, maybe for three x's.
Mhm.
If you have three different x values, you have three different critical numbers.
Okay.
Is clear?
Yeah, I got that.
So note that there is no value of x for derivative that we just found when derivative equals 0, since the numerator is always positive, right? However, f prime of x is undefined for x -2, right? Since initial function for -2 equals 0 and x equals -2 is in the domain of a function. Because initial function is defined for this value of x, right? Guys,
Yeah.
if we would get undefined here again, if it would be undefined for x -2, it means it doesn't work. But this point is within the domain, right?
Yeah.
Of our initial function. So we determine this point as a critical one, and we now, what are we doing next? Determining the slopes of tangents for x values close to this point, as we did before, to the left and right.
Okay. Yeah, that makes sense.
So here you can see the example. This is values of x to the left from -2, and this is values of x to the right from -2. This is just the copy of the derivative that we had, right?
Yeah.
Just two same columns. And this is the value of the derivative for a corresponding value of x. Is it clear?
Yeah.
Mhm.
So now let's analyze this table. Let's take a look at it. What we see here. Yusuf, can you answer me?
For this table here.
For this table, yeah. And just what can you take from it? What you see? No
Hmm,
worry, there is no wrong answer.
I'm not sure exactly.
Take a minute. We
Well,
have
it's a value table. It's stating the values for.
yeah. It also gives us a signs.
Yeah, it gives us.
It also, for example, I can see this value is far away from this value.
Yeah. And same thing with the x values too.
So, and what is this value? What is this? It's a value of slope of a tangent line, right? It's a value
okay,
of
yeah.
derivative.
Yeah.
And this is also value of a slope of a tangent line.
Yeah. And that's the value of the x.
So I keep thinking, we're on the right track. So we can see that the derivative to the left side from this value is negative, and to the right side, it's positive.
Yeah.
Okay, so let's move on. I'm going to explain this now. So let's read first. The slope of the tangent is undefined at the point -2, 0. Do you understand why it's -2, 0? -2 is value of x, critical point, and 0 is the value of of initial function in this point.
Okay.
So that's how we find point, or in a critical point, you can call it that way. So it's going to have coordinates -2 and 0. Why 0? So it's x-intercept, right?
Before you explain, can I guess, are we finding the limit?
Pardon?
Are we finding the limit? Is negative?
No.
X equals negative-
Basically, yes. Basically, we're finding value of this function when x travels to -2, basically. But for here, we're testing that we're just basically substituting these values of x in this function, and we are finding basically the limit of this function. You're right.
So x equals -2 is the limit?
No.
Okay.
Limit is operation. It's mathematical operation. Remember, it's limit function basically.
Mhm.
So reason why we're doing this, why we're doing it to the left and right from this point, because we cannot find limit at point -2, because at point -2 this function is not defined. Remember, if the function is not defined in a point, then limit does not exist in this point. But a limit can still exist to the left and right from this point, right? Remember, when we approach this point, we still have some values. Am I right?
Pardon?
I was saying that even though function is not defined in this point, so we cannot find the limit in this point, but we still can find limits from left and right hand side to this point. Am I right?
Yeah.
Yeah.
So one thing that this table tells me, that to the left from this point, I always have negative numbers. You see it?
Yeah.
So my function would decrease. And to the right hand side from this point, I have positive numbers. So my function would increase. But look at the tremendous difference between these two values. Doesn't it look to you like usually we don't have that difference close to point? Let's say I have nice parabola like this. Please look here. And I have point on the top. Let's say this would be a tangent line to the left hand side. The last tangent line to the left hand side would be almost 0, right? Almost 0, almost tangent and horizontal, almost, right?
Yeah.
To the left hand side. And to the right hand side, it would be looking downwards. Yeah, almost close to 0. If we make this small step, look, it's 1/10,000, I guess, 100,000. Imagine if we make a step of 100,000, we usually have a micro mini difference, right?
Yeah.
This would be slightly positive, this would be slightly negative, because this one still looking upward and this one looking downward, right?
Yeah.
But slightly. And what do you see here? Look, nothing kind here. It just jumps. It jumps from negative 30,000 to positive 30,000. Does it make sense?
Yeah.
It still makes sense. We still know where the function goes, whether it's increasing or it's decreasing, right?
Yeah.
But remember, we talked about curves that can be differentiated as the one that you can draw without taking your pen off the paper, right? And without sharp corners. And remember what happened with these sharp corners. This is where we get this type of values, where derivative to the left-hand side and to the right-hand side are drastically different. Is it clear?
Yeah, that makes sense.
So we're a step closer to the solution here. So let's talk it through. We found one critical point for critical number x negative 2, right? In this particular example, the slopes of the tangents to the left of x equals negative 2 are approaching minus infinity. Does it make sense?
Yeah.
So if you keep increasing this value, or like decreasing it, basically, making it even smaller, like, you know, 0.0000000, many zeros, and 1, this number is going to increase. You can see the pattern, right? Tangent line is, slope of a tangent line is increasing, or basically decreasing. But you gotta look at the modular, because modular states for the angle, and sine only states in what direction it looks. So values to the left from x negative 2 are approaching negative infinity, while the slopes to the right of x equals negative 2 are approaching plus infinity, right? It's like a limit to the left and right hand side. Limit to the left hand side approaching negative infinity, to the right hand side approaching positive infinity. Thus, limit does not exist in this point, and derivative does not exist in this point. And that's exactly what we found in the previous step. We said that derivative is undefined for x equals negative 2. Remember here, because it's going to result in denominator equals 0. Make sense?
Yeah.
So, and here we showed again that because of the difference in the limits to the left and right hand side, derivative does not exist again. So since the slopes on opposite sides of x equals negative 2 are not approaching the same value, there is no tangent at x equals negative 2, even though there is a point on the graph. Any questions so far?
No.
No.
So let's read this. If a value c is in the domain of a function f of x, and if this value is such that f prime of c equals 0, or f prime of c is undefined, then c comma f of c, it's a point, that critical point, right?
Yeah.
So it's a critical point of the function f, and c is called a critical number of f. I think it's a mistake they made here. I don't think it should be second derivative. There's a critical number of derivative of a function. In summary, critical points that occur when dy or derivative of y by dx equals 0 gives the locations of horizontal tangents on the graph of a function, right? So when derivative equals 0, it's a horizontal tangent line. Remember. On the other hand, critical points that occur when derivative is undefined give the location of either vertical tangents or cusps. That's exactly what we saw in a previous example when derivative was not defined for x negative 2. We showed cusp. Oh, sorry. We show basically we found we said we found that no tangent exists in this point, right? Because values of the derivative to the left and right hand side are way different. So besides giving the location of besides giving the location of interesting tangents or lack thereof, critical points also determine other interesting features of the graph of a function. So any questions so far? Guys?
No.
No, not really. I think I understood most of that.
So you gotta work it through in the home assignment, but this is really not hard topic.
Yeah.
So please write this down in a short form, okay? For future notes, I would like you to have it. Critical numbers and local extrema. The critical number C determines the location of a local minimum value for a function f if f of C less than f of x for all values of f of x near C. Similarly, the critical number C determines the location of a local maximum value for function if f of C greater than f of x for all values of x near C. Together, local maximum and minimum values of a function are called local extrema. And here you can also include critical number definition, and it's gonna look like this. F prime of C undefined, then C critical point. A critical number, sorry. Let me know once you're done. Ahmad, how are you doing so far? How you like our class? Thank you. Hurry up, guys. We have one more example to cover, and you're gonna be free for weekends. Good job, Ahmad.
I got it done.
Give me a second. Okay, got it.
Let me explain you this in another words, okay? So let's take an example where we had two parabolas, right? Let's say one of them looking downwards and the other one looking upwards. In the previous example, we showed, you see that the values close to these critical points to the left and right of our initial function are different. But here, if you take a look at the values of f of x, so y values, right, to the left and right from this point. So here, let's say we have f o c, right? F of critical number. Am I correct? This is, guys, work with me. We're gonna move fast. This point gonna be the local maximum, right? And value of y in this point is f of c, or f of critical number.
Yeah.
And you can see that to the left and right from this point, y f of x is less than f of c for any point to the left and right. And we're looking specifically near f of c because we're calling it local extrema, okay? If you look in the whole domain, it may not be a maximum value, okay? But it's local extrema. On the other hand, in this example, we can see that this point is going to be f of c, and all other values of f of x close to it greater than f of c. Do you see this? To the left and right, y value is greater than f of c.
Yeah, I see it.
So this is exactly what they say here. This is just a natural visualization.
Okay.
Can we move on?
Yeah.
So as mentioned earlier, local minimum value of a function does not have to be the smallest value of the entire domain, just the smallest value in its neighborhood. Similarly, a local maximum value of a function doesn't have to be the largest value in the entire domain, just the largest value in its neighborhood. So local extrema occur graphically as peaks or valleys. The peaks and valleys can be either smooth or sharp. This is what we saw in this example. Here we had sharp valley. Am I right?
Yeah, that makes sense.
So this function, I'm going to plot it for you. This is y, this is x, this is -2, and this function would look like this.
Okay.
Constantly decreasing, you see, negative value of derivative. And here it's increasing, positive value of derivative. Do you see it?
Yeah.
And you can also see, as the closer we get to this point, the steeper it gets. It's basically going to look like this.
Okay.
So that's why it travels to negative infinity to the left-hand side, because you see it's derivative looking downwards and downwards and downwards, steeper and steeper with every step, right?
So does it ever touch -2?
Yeah, derivative does not exist. It's -2, so it means we don't have a tangent line. Because if you try to make a tangent line through this point, we already showed it when we looked into definition of a derivative. You can make this tangent line in any possible angle here. You don't know what angle it is.
Okay.
Right? So function x. Let's move on. Here's the visualization of this function. So to apply this reasoning about peaks and valleys, let's reconsider the graph from previous example. Here is how it looks like, right?
Yeah.
So the function f of x has a local minimum value at x equals -2, which also happens to be a critical value of a function. Every local maximum or minimum value of a function occurs at a critical point of the function. In simple terms, peaks or valleys occur on the graph of a function at places where the tangent to the graph is horizontal, vertical, or doesn't exist. How do we determine whether a critical point yields a local maximum or minimum value of a function without examining the graph of the function? We use the first derivative test to analyze whether the function is increasing or decreasing on either side of the critical point. Is it clear?
Mhm.
So last example for today. Based on the given polynomial function graph, we need to plot derivative of it.
Okay.
We already did something like that in the last class. Let's review solution of this example together.
Okay.
So a polynomial function f is continuous for all values of x in the domain of f. Let's see, verify it. It's in fact continuous. We don't have empty points, right? We don't have any cusps. It's just nice smooth curve. Am I right?
Yeah.
So to graph y equals f prime of x using the graph of y equals f of x, first determine the slopes of the tangent lines f prime of x e at certain values, x values, x e. These x values include zeros, critical numbers, and numbers in each interval where f is increasing or decreasing. So we need to find tangent lines at certain points, right? And these points are going to be such points that are going to include zeros or intercept, right? When x equals 0, y equals 0. It's also going to include critical numbers, a number, at least one number in each interval where f is increasing or decreasing. So if we look at this graph, we're going to have 0 point here, it's y-intercept. We're going to have 0 point here, it's x-intercept. We're going to have a critical number here because it's local maxima, right?
Mhm.
And I'm going to have a critical number here because it's local minima.
Mhm.
We'll also have to take 3 different points on this graph, one before first local extrema, one between first and second local extrema, and one after second local extrema. So we have 3 areas. Let me separate it for you. We basically have 3 regions to evaluate. Is it clear now? Good, easy to see on the what I'm drawing?
Yeah.
Perfect. So we need to examine this region in between and after.
Okay.
So let's move on. Then plot the corresponding ordered pairs on a graph. Draw a smooth curve through these points to complete the graph. The given graph has a local minimum at 0, 1. So x0, y equals 1. This is the point. Do you see it? Guys,
Yeah, I see.
this one.
Mhm.
0 and 1.
Yeah.
And local maximum at 1 and 2.
Yeah.
1 and 2. I want you in your assignments give coordinates of these points, okay?
Okay.
So at this point, the tangents are horizontal. Makes perfect sense. Therefore, derivative at this point would be equal 0. So when x equals 0 and x equals 1, derivative equals 0. Make sense?
Yes.
So if we look into function of the derivative, we have point x equals 0, f prime of 0 is also 0. So y coordinate is going to be 0 in this point, right? Look here. This is exactly what we're going to plot later. Point
Right.
0, 0. Make sense? Another point would be when x equals 1, f prime of 1 equals 0 again. And this is the second point, second x-intercept for our derivative graph. Am I right?
Yeah.
Imagine we don't have this red line yet. Imagine we found these 2 points and we went ahead and plotted them, right?
Okay.
We marked them on our graphing paper. We marked these 2 points. So at point x equals 1/2, somewhere here, right? Confirm? Which is halfway between x equals 0 and x equals 1. The slope of the tangent is about 2/3. So derivative would be 2/3. I don't know how they evaluated it approximately, but I agree that derivative is going to have positive sign. Do you agree with me?
Yeah.
Because it's growing on this period. So
Yeah.
here function is growing, here it's decreasing, and here it's decreasing again.
Yeah.
Decreasing, growing, decreasing. Another reasoning about local minima and local maxima, right? So the function f of x is decreasing when f prime of x less than 0. The tangent lines show that f of x less than 0 when x less than 0, right? All right. Derivative less than 0, so decreasing when to the left of x equals 0. This interval.
Yeah.
And when x greater than 1, again, decreasing here and here. So derivative would be less than 0. Negative sign. Similarly, f of x is increasing when f prime of x greater than 0. The tangent lines show that f prime of x greater than 0 when in interval from 0 to 1. Here. Do you see it?
Yeah.
So let's go to our derivative. We know that in this area, it should be positive, right?
Yeah.
And in these two intervals, it should be negative. And before you even plot the graph, take a look at what they're going to give us. You see that derivative is negative here, and it's negative here, and it's positive here. Am I right?
Yeah.
So the shape of the graph of f of x suggests that f of x is a cubic polynomial with a negative leading coefficient. You can make such a statement based on knowledge about cubic forms or exponential polynomial functions. Basically, it works in such way: if you have x squared, you're gonna have one local minima or local maxima, right? Like parabola. When you have cubic form, usually you have 2 of those points. And that's what we see here in this example. If it would be 5th power, it would also have its specific number of critical points. So with a negative leading coefficient, so if we know it's a cubic polynomial with a negative leading coefficient, so we can assume it can look like negative x to the 3rd power, right? Guys? negative x to the third power. In this fact, it has a little vertical displacement because we don't have 0.00, but it doesn't matter because when we take derivative, we don't care about terms, right? We don't care about constants because constants are going to turn into 0 when we differentiate. And when we differentiate things that look like this, we're going to get still negative coefficient and second power. So what it means? It means it's going to be parabola looking downwards.
Yeah.
Am I right? Great. So with this suggestion, the derivative f prime of x may be a quadratic function with a negative leading coefficient. If it is the graph of f prime of x, it's a parabola that opens down. So now, final step, when you came to conclusion how this derivative should look like, now you're ready to plot it. You have 0.00 right here, you have 0.10 right here, and you have 0.1/2 and 2/3. Remember, somewhere in between these two critical points.
Okay.
So now, these points are sufficient to plot this graph because we know it's a parabola that passes the 3 points and facing downwards. And remember, 3 points is enough to plot parabola for you. Remember?
Yeah.
So, yeah, we know that now we basically define how the derivative function should look like. So here are the key ideas of our today's class. You can access all of this material in your course shell on the Google Drive. Please review this material by yourself at home to make it clear for yourself what are we talking about.